So recall back to the early on in the class we talked about there was even when we were before we even got to actually making a network, right? We were just talking day-to-day communication. We chose packet sizes that were how big? Remember?
Twice the length.
Twice the bandwidth delay product, right? So what we were choosing in that case is we were choosing a packet so that if we heard something on the network collide, then the network wouldn't be idle, right? We were trying to come up with the maximum amount of fill to the network. Now, of course, when we're doing internetworking, right, our packets are going to be much smaller than our bandwidth delay, twice our bandwidth delay product, right? They're going to be much smaller because we have different types of networks and they have different data link layers, and we already discussed that we already choose the smallest one when we go across, right? So in that sense, if our network is much, much larger, our packets look like this, right, going across the network. Well, that poses a real big problem for our very simple stop and wait protocol that we use for retransmissions on networks that actually did retransmissions, right? So remember, on a stop and wait protocol, we sent a packet this direction, right? And then after it was received, so this would be data, after it was received, there would be an ACK sent. However, now we're sending across the internet, right? And so in terms of delay, in terms of distance, right, it can vary widely. One, we have a limitation on maximum packet size because of the data link layer and everything in between. So what do? How bad is it, first of all?
Not bad.
Huh?
Not bad.
It's not bad because doing anything else is just more work, right? Let's see. So let's pick a terrible internet connection, right? So UCCS wants you to stay off of Google and YouTube and everything, so they limit their external bandwidth to 1 megabit per second, right? That'd be an awful connection, right? We all admit that. Right, if you're going to go to UCCS services, of course you get all that you want, right? But let's just say that we limit it to 1 megabit per second. Right, which is terrible, right? And who has a computer open? Ping Google. How long do you think it's going to take to ping Google?
I'm going to go with 56 milliseconds.
56 milliseconds. All right, so we'll just choose that. 56 is a horrible number to do math with right out of your head. So
64.
Or let's just do 50. Right? So let's just do 50 milliseconds. All right. 50 milliseconds ping time, that is round trip time, right? So that is twice the delay to get to Google. Google's fairly local, right? It's here in the United States, right? So it's fairly local. Now, we are going to pick, let's say we traverse.
5 to 6.5.
Huh?
It's 5 to 6.5.
Oh, 5 to 6.5. Well, that's better.
Wow,
Let's just
way
use
off.
5. That's way better. Let's just use 5. That's fine. All right. So we have 1 megabit per second, and we have 5 millisecond round trip time, right? And we're going to pick. I'm going to pick this because it's really easy. 1,250 bytes packet size. Not realistic because we're going to run into some 900s and stuff across, right? But the nice thing about 1,250 bytes is that it's also 10,000 bits, right? So that makes my math easier. So now we have a 10 kilobit packet that's crossing across the network, right? How long does it take to get our ACK? 5 milliseconds, right? right? Because when you ping, it's a round trip time, right? So it takes 2.5 milliseconds to get to Google, 2.5 milliseconds to get back. Right? If we're sending every 10 kilobits every 5 milliseconds, how much data is that? Well, in 1 second, right, that'd be 20 times that, right?
200 times?
Or 200 times.
2 megs?
Huh?
2 megs?
2 megs. 2 megabits per second. Well, that's not too bad. Right? So that means that we can fill this pipe. So UCCS's arbitrary limit is still limiting us. Now UCCS comes out with a policy that says, oh no, we're going to give you 10. Right? Does it actually help you at all?
No.
Well, kinda. You get double, right? Because you can still get 2 megabits per second, right? But you're not filling the 10. Right? Then the student government comes out and does a protest and they give you 100. Right? None of this matters anymore. Right? Because you can only send now you're now limited on the stop and wait protocol. So even if you had a gig line, won't matter, right? Because you can only, because the way that you're sending packets across the network, because they're much smaller than the bandwidth delay product, 2 times the bandwidth delay product. So it would be nice if we could have a method that essentially fills our pipe like we did back with the data layer. We would like our pipe to be filled with 2 times the bandwidth delay product. So the answer is, instead of doing stop and wait, let's send more than 1 packet. Right? What we would like is all these little packets to be back to back, going across the network. And then of course the ACKs are going to be back to back. But that means that you're now going to be getting ACKed for packets that you sent, you know, not that you sent 10, 20, 30, 100 times ago. Right?
This is assuming full duplex?
Yes. 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 And in modern networks, it's usually full duplex. Right? Even though your bandwidth might be smaller one direction, the delay is the same. So, but ACKs are usually small, so that doesn't really matter. So, in fact, in most of this class, we assume the ACK is 0, sizes of 0, because it just makes the math easier. So, what we would like is we'd like to send more than 1. But how do we go about doing that?
You have to buffer.
Huh?
You have to buffer.
Okay, yes, we're going to have to buffer. You are exactly right. We're going to have to create a buffer. So for right now, let's just start out with the send buffer. So this is just simply at the transport layer, right? We're not dealing with anything at the network layer right now. At the transport layer, we fill a buffer window, right, when we write. So let's say, let's just fill the first one, right? We fill the first one, right, and our program continues writing, fill in the second one, fill in the third one, fill in the fourth one, fill in the fifth one. Now let's assume that we did the math on our bandwidth delay product and that we can do 5 windows. Right? And at 5 windows, the network is full. So we're going to set W equal to 5. And after we hit 5, we no longer send any packets, right, until we get an acknowledgement. Every time we get an acknowledgement, right, we forget that packet and we are allowed to write another packet to the buffer. So it's the networking layer down here that's sending the packets out. Right, so we just assume that is however fast it goes. And then TCP is managing this buffer. So in order to do this, what kind of variables do we need to keep track of? Remember with stop and wait, all we needed is a 1-bit sequence number, right? Send 1, send 0, send 1, send 0, send 1, send 0. Because you couldn't send 1 unless you got an ACK for 0, and you can't send 0 unless you get an ACK for 1. So now we need something different. So 1, we're going to need a much larger sequence number. In fact, depending on what protocol, you might need 2 times the window size for sequences, depending on what protocol you're using. Right? For a very simple go back in, you need the window size plus 1. Because you can have an ACK on the wire, and then as we get to selective repeat, you need 2 times the window size. So what happens is when we send one, we keep a pointer internally, and TCP keeps a pointer on last ACK received, right? And then we have our window here. This is W. And then we'll have another pointer of when things are available. In this case, it's not. Right? We'll have a pointer to available. Actually, I think it's last frame sent or last segment sent. So last ACK received and last segment sent. Now last segment sent can never be larger than our window size. So last segment sent subtracted with last ACK received. And so we have a sliding window, first in, first out buffer. Right? In reality, these are implemented in a circular buffer. Right? But for ease of education, let's just make it a linear buffer. And then every time that we get an ACK, we move last ACK received to the next window. Of course, this shifts our window over to here, and now we have an available space. And so this is now, this was subtracted by this is now less than W, so we can write again. Super simple, right? What's happening at the receiving side? The same thing. The negotiation for the connection set up the window size, so we still have a window of 5. Let's do it in the middle of the communication. And we still have a window of 5, right? So as these things start coming in, right, then we'll have a pointer to next, like data. And then we may also have another pointer to last ACK sent. Now TCP is going to send the ACK right off the bat, right? So now the question becomes, what happens if this buffer gets full? The receiving buffer gets full. And how could that happen?
If you're getting more packets than you can process, you get full and then you just drop them.
Yes. The simplest answer is if you get more packets than you can process, you drop them. Right? And if you drop them, then you're not sending an ACK back. Right? And if you're not sending an ACK back, then what happens on this side? On the sender side?
Some sort of timeout.
Yeah. Right? And then we'll do what?
Either resend or.
Usually on timeouts, you just reset. In fact, in general, that's going to be our entire control mechanism. Is not telling somebody that we're full, is not telling somebody that we're empty. Right? So a lack of an acknowledgement, right, is going to be used for all sorts of things. So in this case, if this was happening, then essentially you have a fast server on this side, maybe a slow mobile device on this side, and is feeding data faster than the application can read it. Right? And if the application can't read it, its buffer gets full, right, and it quits sending acknowledgments. If it quits sending acknowledgments, essentially the sender gets stuck, right, of just sending duplicate packets. In a very simple case, this is fine, right? Awful use of networking, but it's fine because it still guarantees that the packets are received in order, which is what a reliable transport has to do. So the service a reliable transport provides, in this case, we're getting close to TCP now, is packets in order, right? A bit stream. And so it's still doing that, right? We're clogging up the network, but we're still doing it. Is there a better way to manage this?
Sliding window?
Huh?
Sliding window.
Well, this is sliding window. But is there a better way to manage it?
Adjust the size of the window on the fly.
So in reality, right, we're using big clunky block windows. In reality, TCP uses byte bounders, right? It can send an arbitrary number of bytes, right, up to the negotiated window size, right? But it's just easier if we use Windows, right? So where we have Windows, what we could do is when we send ACK backs, we could tell the sender how much space we have. So on this in the way that the state is now, right, on this last ACK sent, right, we have this one right here available. Right? So on our ACK, we could send an ACK window equals 1. So ACK with the sequence number, whatever it is, and window of 1. Right? And then when this ACK returns here and arrives, now TCP says, okay, I can send one window. Now, what happens if it's full? Let's say this is full, right? So now it would send back an ACK where the window equals 0. So now this arrives at the sender, and the sender knows that it can no longer send any messages because the buffer is full. So now we solved our network problem, because even though this thing is going to time out, it is essentially blocked because the window is 0. We have a new problem, right, is now it's on the receiver's duty to send a duplicate ACK when this thing gets rid of one, right, with an ACK equals 0. And this is a duplicate ACK, right? It has the same sequence number. Or, no, it's 1. Sorry. And that will unblock the sender and allow it to send 1. And it's actually, in implementation, it's way more complicated than that because we're doing it on byte boundaries. Right, so right now we have these big giant windows, but TCP can take an arbitrary number of bytes. So what will happen is, like, let's say that our window is 1270, or let's do 1024. Let's say that each of our windows is 1024, then we would send back a window of 1024. And it can send 1024 bytes. Right, let's say that you do a receive, right, and the receive actually pulls out 3K. Or in that case, I guess it's 1.5K. Right? Then our window going back would be 1.5K. And the other side could send 1.5K. So the TCP does not preserve segment boundaries. So once it's in the queue, it's just a byte stream, right? And all segments of how it actually got transported across the network is lost, right? And now you just have a buffer with a pointer at the end of the buffer and a pointer at the beginning of the buffer, and that's it, which allows you to calculate a size to read things out. When you call receive in your socket, receive can ask for more than a segment size. It can ask for less than a segment size, right? You can ask for the world, and it will just give you everything that's in there and return what the size of what it gave you. So one receive call could clear out this entire buffer. You could call receive with 10 megs, right, of allocated space, and it just clears the buffer out because TCP buffer is not 10 megs. So what does that look like on our little time diagram? So let's start with a stop and wait first. So we have our client and our server, right? Let's say we're simple communication, we're having our client upload a file, right? Just pushing stuff. Magically, our sequence is going to start with 0, right? Remember, it starts with a random number, but we're just going to start with 0. So what do? We do our handshake, and then we have this direction. We have basically x plus 0. This is our sequence number. And then what does our server return? It returns x plus 1, right, with what? However big the window is, right? So let's say we had a 4K window on this side, right? That means there's probably a 4K window on this side, right? And so let's say that it sent 2K. If it sent 2K, right, then our sequence, because in real TCP, your sequence number is x plus 2K plus 1. right? And our window equals 2K, because we filled half of that up. Let's say that our application is slow on that side, right? So TCP sends this, right? So now it's good, our sequence of numbers is going to be x plus 2k plus 1, right? And we're going to send 2k again, right? So now our buffer is completely full, right? It's going to be x plus 4k plus 1, and our window is going to be 0. And then our buffer, we finally call receive on this side, right? We're going to send x plus 4k plus 1 with a window of 2k. And it will continue on and on and on and on. So this is flow control. So there's a difference between congestion control. So congestion control is where the network is failing to transmit packets, right? Flow control is where the buffer on the receiving end is full. Both actually throttle back the amount of data that's being sent. Right? Because you can imagine, like, if you had a business connection that had a 50 megabit per second upload, right? You could push too much data to somebody. Easy. Networks are fast enough today where LANs can actually overcome hard drives. And you can actually push more data over the network than your hard drive can write to disk, particularly for spinning disks, right? So this is not unrealistic, right? You can just put a lot of data across a network and there's nothing the computer can do with it fast enough, right? So there needs to be some mechanism for that to be throttled back. That's flow control. Now the question is, what do we do when we don't get an ACK and we have a timeout and it has nothing to do with the window size now being blocked? Right? What if something's actually lost in the network, corrupted in the network, something else? What do we do? First, what is the sign that we get? Or infer in this case. So you send a packet across the network, right? How do you know it's lost? You don't get an ACK back, right? But now, which would be fine to stop and wait, but now we've sent many packets across the network, right? So what are some strategies to retransmit the packets, right? The packet's been lost because we presume it's been lost because we didn't get an ACK. What's the strategy? So the first strategy is to just look at last ACK received, right? And we start resending from there. We just rewind the entire buffer, which is fine, we still have them, right? Remember that in a window of 5, right, where it's a circular buffer, these have not been overwritten yet. So we still have them, so we just rewind the buffer, right, and we send those again. And if we do that, that's called go back in. Which is funny, because in the documentation it actually refers to W, and then the algorithms go back in, but it's go back W, but the algorithm is called go back in. All right, we rewind the window to the last ACK received, and then send them all back. What's the advantages? Huh? It's easy, right? Way easier than selective repeat, which is filling in the missing packets in the middle of the buffers, right? Way easier than selective repeat. And as you go through, most everybody in this classroom will do go back in because it's easier. What's the disadvantage?
If you lose just one packet, you're sending the entire number again.
Yes, right? In reality, our window isn't 5, right? It's usually more like, if you're going like cross country or over to Europe or something, it might be hundreds. If you look at like just the delay to Spain is like 200 milliseconds round trip time. So now you have a 200 millisecond plus whatever your bandwidth, right? Right, that's a lot of packets being sent 1,250 at a time, a lot. The network capacity is very high. But it's easy, simple on both ends, right? The other strategy is to find the missing packet, right, and retransmit it. Are there any disadvantages to that other than it being harder to program? Your sequence numbers have to be bigger. We already discussed that. Anything else?
Well, if it happens a lot, then you have a snowball effect.
Yes. Well, the other thing is you have to keep 2 buffers. So you're going to have, because remember we have this flow control thing on one end also, right? So we have things not being pulled off, right? And then there might be missing packets inside of there, right? So we need to keep a state of 1 buffer for our selective repeat, and then we need a buffer for how pass that up to another buffer that receive can take from. Could be implemented with 1 buffer, right, with lots of different variables pointing in there, right? But the idea is the same. It's just way more complex, and it's likely to cause more storage issues. But you can find missing packets. It does introduce one more problem, though, and that problem is if you don't do any heuristics, you've basically turned your network into stop and wait again, because you got the full length of the network from one side to the other, right, to figure out that now you need to replace a middle packet, right? But if you've lost one packet, then it's very likely you've lost another, right? And so now you need to wait again for that to come back. So we have to come up with a strategy that makes it much more efficient. And the efficient is to do optional acknowledgements. So what we do instead is we send back the ACK. We also send back the window, like we talked about before. But we also send back up to 3 optional acknowledgements. So like, let's say you received packet 100 or segment 100. Right? And then, because we're measuring bytes now, because we're dealing with real TCP, right, 200 is lost in the network. We know that because we're the network gods. But let's look at what happens if 200 is lost. So 100 has been received, right? In straight go back, or straight selective repeat, right, what are you going to acknowledge? Are you going to acknowledge if 200 is lost and byte 300 to 400 comes in, are you acknowledging 300? Right? Are you going to acknowledge 100 again? Right? Or are you going to acknowledge both? And the answer is you should probably acknowledge both. So the 100 to 200 comes in, right? You send an acknowledgement. 200 gets to 300 gets lost, right? 300 to 400 gets comes in. You send an acknowledgement for 100 again, and you also say, oh, and by the way, I've received 200 and 300, or 300 and 400, right? And then 400 to 500 comes in. You send an acknowledgement for 100 again. But you also say, hey, I've now received 300 to 500. The optional acknowledgement is a range, right? And then you get another packet. All these packets were already on the wire, right? So they're still coming in. And so the next one comes in, and you send an acknowledgement for 100, a duplicate acknowledgement for the third time, so the fourth 100 acknowledgement, right? And you also send the optional acknowledgement for 300 to now 600, right? And on that point, TCP resends the packet. And so now that packet is traveling out of order through the network, and however long it takes to get there, and then the receiving actually does the selective repeat and actually sticks it in the correct place in the buffer. That buffer then becomes available for receive. Notice receive at any time could have called that 100 point, right, and took that first 100 bytes, right? But it would be blocked from taking any other bytes until that missing packet was put in there, because there's no capability for receive to like select parts out of the buffer, right? It's really a take out of the buffer, and once it's taken by receive, the buffer is cleared. So you can't like pre-process anything, whatever. So it comes through. Now there's up to 3 optional acknowledgments, so we can have missing packets in there also. Let's say that the network, for whatever reason, is really bad right now, right? So we could have an optional acknowledgement for 200 to 300, and then the 300 to 400 packet is lost, right? Then we could have another optional acknowledgement for 400 to 500, and then the next packet is lost, so there's this gap, and we can have up to 3 of those. And that way, now it only takes 3 duplicate acknowledgments to go through with those missing packets before TCP just fires a GET, way before the timeout would have happened to get across the round trip time across the network. Way before. Because usually it's 10, 20, 30 packets, right, and that are on the network at any one point in a communication. So now it only takes 4 packets, 3 duplicates, which is confusing. But in the documentation, it's 3 duplicates. So 4 packets. And then we resend, right? And then we just have to programmatically stick them in the right place of the buffer, change the pointers for the ends of the boundaries for receive to be able to pull everything out.
So they're only resending the data that was lost, correct?
Correct. Just that range. Remember, TCP, we've been talking in terms of windows, right? TCP actually sends in range of bytes, right? So in reality, you're looking at ranges of bytes. Got it? So the next question is, how the hell do we come up with the timeout window? If things are going to time out, how do we come up with that? In a local network, it's super easy, right? Usually in a local network, the timeouts are you're only sending 1 packet at a time because that's the width of the network, or double the width of the network, right? So the timeouts become easily to predict and arbitrary, right? Or not arbitrary, design specific for whatever you're using. So if you're using gigabit LAN, right, the timeout is X, it's in the spec, right? You know how long it takes to get across the network to timeout. How long does it take to get across the internet? Who knows? Who knows, right? So you were pinging Google, it was between 5 and 6, right? But if we pinged it for a while, we get some crazy like 10, 20 millisecond ping. Right? So now we have the same location, presumably the same distance, though they could take different routes, particularly with ping through the internet, but presumably the same distance, right? And we're getting wildly different times. So how do we pick out a timeout value if I can't ask you, give me a math problem that tells me the current timeout for Google or whatever?
4 to 7 now.
It's 4 to 7 now, right? So that's actually a good example, right? So it's almost doubling, right? Even though the times are small, they're still doubling from max to min. How do we pick a timeout? What are some easy ones?
Can't you measure?
Huh?
Can't you
We could surely measure, right?
Measure
You
round
just
trip.
measured it with ping.
Yeah, measure round trip and then take an average.
So we measured round trip, take an average.
Double it.
That's definitely the easiest one, right? Let's measure round trip and take an average. Let's see what that looks like. This is Netflix time.
You almost have to do a min-max to do it.
Oh,
Over
yeah.
time.
Right? So we have real time on this time, round trip time for packets for segments on this time. Right, so this is our network, right? So this is Netflix time. Right here, where the thing gets really congested. So how do we actually pick an average, right? So we could take the min right here and the max right here, right? And we could average it, right? So that would be like this. What does that look like?
Like trouble.
It looks like very sad Netflix time. For everybody in the world, by the way, right? Very sad Netflix time for everybody in the world, right? So if we do this, what happens here, this place where above this our timeout line, what happens?
Packets just get dropped.
They get dropped and they get resent, right? So if this is network congestion, which we will spend most of the next week, actually following the midterm we will talk about, right? If this is congestion and you're resending the packets, you're making the problem worse, not better, right? So everybody, this is Netflix time, everybody in the world's doing this. So we are now all sending packets because we're hitting timeouts.
You gotta go with max.
Huh?
You gotta go
Oh,
with
so we
max.
can go with max, right?
Well, you gotta go with maxes over time, over like some amount
Like
of
a
time.
rolling max.
Huh?
A
Yeah.
Double max. Double max you're gonna.
So the question here is, we're the network gods and we can obviously see into the future, right? Or maybe we measured yesterday's Netflix time so we could predict today's Netflix time, right? But the problem with this is now, so while you would never, in this case, if you pick this max line, you would never lose packets because of congestion anymore, if everybody's picking the same line, right? There'll definitely be some cheaters, right? But the problem is, like, you can lose packets for other reasons, right? You can lose packets for corruption, right? So if packets get corrupted, now you still have to resend those. And now you have this crazy long delay in sending, because now every time there is a lost packet, we gotta wait this delay time to send it.
So
How much is the,
time sync?
Huh?
how much is it in the real world?
The real one.
In the real world, this actually is taken out of the book from a real world example. So in the book, this is like from Washington to I think it's Barcelona, and this is 200 milliseconds here, and this is 900 here. That's almost a second. That's a long time on a network, right? That's a long time, right? So what we would like though, you know, we would like something that would look like this, right? That's what we would like. And it turns out we can actually get something close to that. Right? So we could take an average, we take a rolling average. So what's a rolling average?
You take a sample of time, take the average, and then when time moves forward, you take another sample.
And average it with that average, right? So if we took a rolling average, what would it look like? Just a simple rolling average.
Like trend line.
Oh, it would. It would look something like,
Not that big. Could be. Wouldn't be no.
it would look like this. Which is, it's close, but it's too little too late, right? Is there something else we could do? Intuitively looking at this,
Dynamically change?
right, what can you say about this graph?
Well, it's got a spike in it.
It's got a spike in it. How do we see, mathematically, how do we say it's got a spike in it? Yeah. It's somewhat like the bell curve, but sad in the middle. Right? What it is right here, right? If we took this right here and we didn't look at the rolling average, we looked at the amount of change in the graph. It has a large spike of change, right? It has another large spike of change here, another large spike of change here, another large spike of change here. So what, you know, the spike of change is called velocity. Right? So here, there are places in this graph where the velocity is changing greatly. It's actually a really neat PhD project that was done here at UCCS on using velocity and rolling averages, just like TCP, to predict epileptic seizures. And they actually did really good at it. Right? So instead of trying to look at the average, right, look at the amount of change that's happened. So we're going to use both. We're going to use rolling average, and we're going to use the amount of change that is happening. So what we're going to do is our timeout time is going to look something like an average of the a rolling average. Let's just say average round trip time. And then we're going to add a average change, or the velocity. So, and through experimentation, there's no better way to say that. There's no great math that genius has sat back behind it. They looked at experimentation, and you can see, you can tell it was both optimized for computers because it's all going to be 1s, 2s, and 4s, right? Because that all is just shifting bits. And what we're going to do is we're going to take 90% of the average, the current rolling average, and we're going to add 4 times the average change. So what's the average change? We know what the rolling average is.
Difference between the difference. Right?
Yeah, yeah. So you have the average round trip time, but you also just saved the last round trip time, right? And then we have the current round trip time. Right? Subtract those. Hey, average change. Well, that's at least change, right? And then we keep track of average change as it goes. So what will happen is, if the round trip, the current round trip time is much larger than the last round trip time, right? Then average goes up quickly. If it's smaller, then the number becomes negative, right? And it goes down quickly. And with that, you get something that looks like this. Doesn't mean it'll be perfect. Some things, particularly, it actually would probably do pretty well there, because it's actually not that much of a difference, but it'd probably look like something like that. The first giant spike that came out of nowhere, you might miss a packet. Right? But subsequent spikes that are the same height, because it increases so sharply, and it tends to actually slow down slower than it increases, right? So it just makes that bell wider. And we just keep track of that. So now our timeout values are dynamic. Because we have a way to measure in every circumstance except for a lost packet, we have a way to measure how long it took for our packet to get to the network and the acknowledgement to get back, right? We have a clock. We have an acknowledgement clock. Right? Now TCP, even if there's flow control stuff happening underneath, right, where the application isn't taking it, TCP is still sending the ACKs, right? So as it changed, TCP will send ACKs. And so because we're receiving the ACKs, we can now figure out what the round trip time is on at least that packet, right? And we can now calculate the sliding average, or rolling average, with that increases sharply because of velocity in the graph. Interestingly enough, what is this time? Right here. Kind of messed up my graph, right? What's the bottom of all this?
The RTT for the most efficient.
Correct. That is the real round trip time. Right? That is the delay in the network due to medium and speed of light. Could never be faster than that, right? Because physics would have to change. And that is basically all of TCP other than congestion control. So TCP uses selective repeat with optional acknowledgements, right? The service it provides is a bit stream, right? So that means that there's no real windows, even though we talk about it in class because it's easier to learn it in ideas of windows. But it just sends arbitrary number of bytes up to the maximum window size, right? And then reads out arbitrary bytes on the other side. Because it's a bit stream. This is different than a datagram, right? A datagram actually has boundaries, right? Or boundaries, right? Because they could be out of order, so we might need to shuffle them back in order, maybe. Sometimes we just don't drop them, right? And they certainly could be missing. Anything else that, any questions on TCP other than congestion control? So, right, we did flow control, which is endpoint issues. Congestion control will be network issues. And you'll find out that it is largely the same. We're just gonna add some, one new fancy new trick on top of it to max out the network. All right, that's all I got.